All right, so let's just start going over this now. So again, reminder, this is essentially, she starts with 66,000 in student loans and she's paying them off every month. 1,100 goes towards it every month. And we want to take this equation that we found last time and find and interpret both of the intercepts. So we've got two of them. I'm going to go slightly quicker because you should have already had some time to try it, but as always, if you need to stop me, please do so. And this was technically a D value in the given question, so I'm going to call it the D-intercept. So remember, whenever you're finding an intercept, you essentially let the other value in the equation be 0. So we're going to let 0 be put in for D for the T-intercept. But add the 1,100 over to the other side. Divide both sides by the 1,100, and you will get 60. And this is the time that she's been paying them, so this will be in months. And actually what I'll do is I'll do the interpretation at the very end. So I'll find both of the values and then I'll interpret them over here. And then for the D-intercept, take the other variable, which is T in this case, and let it be equal to 0. So 66,000 minus 1,100 times 0. We'll get 66,000, and that was in dollars. So now we've got to interpret the two. Remember, these are two completely separate entities. They have nothing to do with each other, so you need essentially two separate sentences, if you will. I'm going to start with the D-intercept, actually, and that would be something like, so it's essentially 0 months, $66,000. Again, I never really like saying after 0 months or something like that, so I would just say something like, oh, it's lagging. Let me try to unshare and reshare. That sometimes helps the lag. But it's not lagging on my screen, so just like she did, if it's ever lagging for you guys, let me know, because sometimes my screen doesn't lag, but yours does. All right. D-intercept interpretation. So 0 months, $66,000. So I would say something like before she even pays. So before paying anything. Kayla has $66,000 in student loans. And then for the T-intercept, it's essentially 60 months, $0. So essentially the time it takes for her to pay off the loan. And you could say something like that. You could say something like it takes 60 months for her to pay off the loan. I'm just going to go ahead and be a bit more generic and just say after 60 months. Whoa. Kayla will have paid off her loan. Loans. I don't remember if she had multiple ones. Loans. Again, you could say something like after 60 months, Kayla will have $0 left in student loans. I don't really care how you phrase it as long as it gets the point across of the two separate pieces of that point. So you have to say something about 0 months. Sorry, well, for the first one, 0 months, $66,000, and for the second one, 60 months, $0. But how you phrase that is up to you. I pretty much accept anything as long as it gets the point across correctly. Questions, concerns on the warm-up? All right. I'll try to leave that in there a little bit while I start writing down these definitions, and I'll hold on another like 5 seconds before I start, in case people are still writing stuff down. I started recording, right? Yes, but it's also being weird. Seems fine, hopefully. Anyway, so a definition. A function is increasing if the values of f of x are increasing. Imagine that. As the values of x increase. So, we've got, that was supposed to be a straight line. We've got a couple options. It could also kind of curve a little bit. As long as essentially as you move from left to right, the y values are getting larger. And so remember, f of x is pretty much synonymous with y. So if you prefer to think about it as the y values are increasing instead of saying f of x to yourself, perfectly fine. They're pretty much synonymous. It just depends on the variables in the question. But if it helps you, you can always think of f of x as a y. And a function is decreasing if the values of f of x are decreasing. As the values of x increase, the x values are still increasing. So, there are a couple options for that too. Curve a little bit. As long as the y values are getting smaller as we move from left to right. So we are always viewing these as x increases. You have to finagle some stuff around if you want to make x decrease, because essentially if x is decreasing, the things flip-flop. So we are going to take the generic idea of always just viewing our x values as increasing and then just looking at the y values. And then this one runs into a little too far down. A function is constant if the values of f of x are constant as the values of f of x, of x increase. And that we kind of only got one option. It just goes straight across, horizontal, left to right. All right, I'll wait a couple seconds for you to get that down before we move on to some examples. So, scrolling. Determine whether each table below represents an increasing or a decreasing function. So notice that all of the values here in terms of t, I will probably accidentally say x a lot. Will my laptop get angry again? No, it didn't. Yes? No. No, it's fine. Except it's, oh no. Come on, there we go, sorry. So all of these values are in terms of t. I might accidentally say x a lot, but those t values are essentially an x. So for this first one, if we look at those t values, because remember for all of these definitions, whatever the x variable is, in this case it's a t, have to be increasing. But in this first table they are. -2 increases to 0, increases to 2, increases to 4. So we're set up correctly. So now we can go ahead and look at what our h of t values are doing, what are essentially our y values. And so -8 to 0, that's going up. 0 to 8. That increases. 8 to 64, that increases. We don't care that it increases by different values, by the way. We just care about the values getting larger or smaller. So since those y values, those h of t values are getting larger as we move from left to right, this is going to be an increasing function. Increasing function. Now part B, the one below it, is a little tricky, because if you look at the r of t values, you'll probably say that it's increasing. But we need to make sure that we're looking at increasing t values, which if you look at the t values, they're actually listed in decreasing order. So since the t values are decreasing, you could technically just try to flip-flop the definitions around in your head, but this table is small enough that let's just go ahead and rewrite it in terms of increasing t values. So let's essentially flip it around. So we're going to flip this guy. So 20, 15, 10, 5. And now that we've flipped it around so that the t values are increasing as they should based off of our definitions, now the r of t values are decreasing. Well, they were before, but we just might not have recognized it because the table was in the wrong order. So since the R of t values are decreasing, this is a decreasing function. For part C, looking at our t values, they are increasing already, so we don't have to do any kind of rearranging. That's great. And our S of t values, now with negatives, remember negatives can be a bit weird, so triple check your brain with negatives. Going from negative 25 to negative 20 is increasing and continues on for the rest of them, negative 20 to negative 15 and negative 15 to negative 10. So those S of t values are increasing. So this is an increasing function. And then part D, let's check our t values. Those are actually decreasing again. So t are decreasing. So again, the table's small enough. Let's just go ahead and flip-flop it over. So negative 72, negative 48, or if you're just good at reading the table backwards, that works too. What? Negative 0. That doesn't make any sense. 20, 15. You are correct. 10, 5. Once again, now that we have the t values going in the correct order, this is going to turn out to be a decreasing function. Now, I don't want you to therefore associate when the t values are decreasing with it being decreasing. That is not the case. It just happened to be both of these examples when the t was decreasing, so was the actual function. That is not the case. The t values being decreasing just meant that we needed to rearrange it before we could figure it out. You could still have a case where the t values are decreasing, you flip the table over, but it's an increasing function. So don't assume that it's based off of the t values. These are all based off of those h of t values, s of t, r of t, m of t values once the t values are set to be increasing. All right, questions, concerns on that one? Hold on for a couple seconds as well before scrolling down in case people need to catch up. All right. Before we go to the next one, we need to, well, before we write the answer for the next one, I need to do a little bit of a side note, because what we're going to do is we're going to write the intervals on which this function is increasing or decreasing. So I need to talk about something called interval notation really quick. So say we wanted to say that we were going between, we were allowing, x values to be between two different values. And we wanted to be able to be equal to the two values on the end. Say we're going, x ranges from 1 to 3 and it can be 1 and it can be 3. Then another way to write that in what's called interval notation would be this way. So you essentially write those two endpoints and you put a bracket around it because we can be equal to that point. Whoops. If you wanted to do essentially the same interval but not allow those kind of endpoints to be the value that you can choose, your interval becomes what's called an open interval and is written in parentheses. Now, I know that that looks a lot like a coordinate point. The context of the problem will tell you whether or not it's a coordinate point or an interval. So that is an unfortunate overlap in notation, but the context of the problem should clear up. Really, there's not many problems where you're going to have to be using coordinate point notation and interval notation at the same time. So usually it is pretty clear. Also, we can do kind of a half and half kind of situation where we include one of the endpoints but not the other endpoint. And it's essentially just with whatever, goodness, I can't talk. Whatever endpoint is included gets a bracket, and whatever one is not included gets a parenthesis. So that's interval notation, going to come up every once in a while throughout the class. So you're going to want to be a little comfortable with it. One thing is that if you ever use infinity, so plus or minus infinity, if it turns up in an interval, always gets a parenthesis. Technically, infinity is not a number, it's a concept. So we can't say we're letting it be equal to infinity. That actually doesn't make any sense. So if you have an infinity in your interval, it always gets a parenthesis. Always. Don't put brackets on infinities. I'll be sad. All right, so if we look back up at this question, on which intervals are the following functions increasing and decreasing? If we look at part A, so remember, we're always looking as the x values increases. So we always essentially want to read this graph from left to right. So if I'm looking at this from left to right, essentially the y values are getting larger, you know, for this first kind of part of it. And then right here, it's actually going to kind of turn around. And once it turns around, oops. Oh my goodness. Stay. That's when the y values essentially start decreasing again, right? We're going down. So we're going to have an increasing piece and a decreasing piece. And notice that there's these little itty bitty arrows at the end of the equation. So this is actually going to go on forever in both directions. So technically, so there's that like first left side of that function that's increasing. Now technically that function goes backwards forever, so it's actually going to go all the way back to negative infinity. Ooh, I need to make one more note. I'll do it in just a second. And we're going to stop at 1. And the reason why it's 1, very important point, is that intervals yep, are always in terms of, I'll even put in a little side note for us. In general, you can have intervals that are in terms of y values, but for everything we will need them for, they're going to be in terms of x values. So if you're not doing a ton of other math in your life, just think that intervals are always in terms of x values. So that's why it's 1, because the x value of 1 is essentially that point where it's going to start turning around. Now, technically, this would also be an acceptable answer, including 1. Now, the reason it doesn't matter, well, it depends on who you talk to. I'm sure there's some mathematicians out there who really think it's one or the other, but generally people come to the consensus that it doesn't quite matter. And here's the reason. Saying that something is increasing or decreasing at a singular point doesn't make any sense. Like if you said that x equals 1 is increasing, that doesn't make any sense because it's literally just a point. How can a point be increasing or decreasing? You have to have an interval, like you have to have at least a little bitty line to be able to say whether it's increasing or decreasing. So the fact that we include or not include 1 in our answer isn't really going to change anything. So either one is fine. And then for decreasing, we essentially are starting at 1 and continuing on forever. So this would be from 1 to infinity. Or again, you could include the 1. I would be consistent, like either always include them or always not include them. Except for the case in this question that we're about to do right in a second, but that one's different. I always exclude them, so I would personally write the ones just in all parentheses, but if you really like the bracket ones, go right ahead. So, for part B, if we look at this from left to right, we're essentially going down, we're going down, we kind of slope, but we're still going down, and then we're still going down, still going down, and still going down. Now, you could try to argue that it's constant at that point right there because, you know, it kind of slopes off and kind of looks like it would be straight right there and then continues going down. But again, saying something is constant or increasing or decreasing at a singular point makes no sense. So we're just going to say that this is decreasing everywhere. Everywhere that this function exists, I should be clear. Now note the difference between this function and the last function, let me zoom in a little bit, is that there's no arrows at the very end. And note that it's like a different thing at each end. So the one over here, how did I phrase this last time? We don't have x equals -2. This is what's called an open circle. So since it's, it's not filled in, exactly, it's not included. So since that circle isn't filled in, that's saying that we can't be equal to -2. So essentially that's going to end up getting a parenthesis because it's not included. Whereas over here with this, I don't like this arrow is getting in my way. With this endpoint right here, we have, quote unquote, x equals 2 because it's what's called a closed point because it's filled in. So since we have, quote unquote, x equals 2, that will be included in our interval. We don't work a lot with open and closed circles in our class, but for this first section, you might see a couple questions on it just to make sure you understand it. But for the most part, we don't deal with that too much. But what that would, what that would mean is that we're just decreasing from -2 with a open parenthesis, again, because it's an open circle, all the way up to +2 with a closed bracket. If that circle at the back was closed, they would both be brackets. If the circle to the right at +2 was open, they would both be parentheses. If there were arrows in both directions, it would be from -infinity to infinity. But no little tiny arrows, so we were stopping at those points. Then part C, excuse me. Part C, as we read this graph from left to right, we're kind of going upwards, we're going upwards, we're going upwards, and then at this point x equals 0 is when we kind of turn around and now start heading down. So in this piece, since it changes, we're going to have an increasing and a decreasing piece. So the y values are increasing on that left piece, essentially. So that's going to give us that we're increasing from -infinity to 0, because remember, we always use the x values. Again, you could include that 0 if you want. I usually don't, but whatever floats your boat. And then that right piece, starting at 0 going on forever, is when our y values start decreasing. So we will be decreasing from 0 to infinity. Or, of course, again, you can include the 0. After this point, I'm probably going to just stick to the parentheses everywhere and not include both of them. This isn't going to come back for a little while, but when we eventually come back to doing interval notation, I'm probably going to default to not including those endpoints. But if you ever want to triple check, just let me know. Questions, concerns? All that. All right. Hold on a couple seconds in case people are catching up. So if you have it in front of your face, you might be slightly confused by this, but we are done this set of notes then. What happens, so there is technically more questions on here, but notice that they all say extra. So there's going to be a couple extra problems at the end of, I believe, almost every section. And I will fill those out and post them on Blackboard in case you want some extra practice. There's a tiny extra bit of information that is not necessary. In this section, that's not really going to happen in any other section. But there's this thing called the vertical line test. You don't really need it, but it's kind of a cheat sheet way. So if you want to look over that. But there's a couple extra problems if you want to look them over. But officially, for the ones we're covering in class, we're done this section. So any questions before I move on to our next set of notes? Also, if you need to pull up the next set of notes, you might want to be doing that. All right. So then we're moving on to linear functions. So essentially what we did in the last section is we looked at functions in general, and now what we're going to do is we're essentially going to start building some specific types of functions. I'm actually going to skip this warm-up problem. We're going to leave that for Wednesday, which is our next class, which I'll talk about later. This is a type of question, and I'll talk about it again towards the end of class. But this is a type of question that will show up on your quiz. So we'll do that we'll do this as a warm-up next time. There's also one like this in the extra problems from the first section, so you can look that over if you want. But we're going to start with some definitions. So, the slope between 2 points is calculated in the following way, and this would be given 2 points like x1, y1, 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 and x2, y2, because I'll be pulling out that notation in a second. And this was on your diagnostic quiz, and most people got it right, so that's awesome. But it's okay if you didn't get it right, also, because we're going over it right now. So sometimes you'll hear it as rise over run. I usually won't say that very often. I'll usually say change in y over change in x, which is what this notation is. This little triangle is a delta, and it usually is used to mean change in whenever you see it in math. And the actual calculation will be y2 minus y1 over x2 minus x1. One thing I did see on the diagnostic quiz is a lot of people flip-flopped it over. You did the x's over the y's, so be careful on that. Change in y over change in x. Now, one thing is that it does not matter which one you make x1, y1 and which one you make x2, y2. You get to pick. The only thing you need to be super careful of is that if you put one of the y values first, you have to put its associated x value first in the denominator. That's the only thing you need to be careful of. Other than that, it doesn't matter which one you pick. A linear function can be put in something called slope-intercept form. There's another form that we'll talk about later. We probably won't get to it today, but we'll talk about it later. Which is y equals mx plus b, which I feel is, in the last couple times I've taught this class, is the one that most people are familiar and most comfortable with. The graph of a linear function is a straight line, where m is going to be the slope of that function. So essentially, if you take any 2 points and use that slope formula, it should give you that. And then b is going to be the y-intercept, which is why it's called slope-intercept form. Maybe I should be a bit more meticulous and say vertical intercept. But since our next problem has some t values in it. So linear functions have a constant slope. That's how we're going to be able to figure out whether or not a function is linear, which is essentially what we're going to do next. We have these tables. We want to figure out if they're linear or not. I'm going to hold on like 5 more seconds. See how I can get those definitions down. And then 1233, 1250, okay. So let me try to leave a little bit in there just in case. So determine whether the following tables could represent a linear function. If it can, find a possible formula for the linear function. If not, explain why. Now there's a couple different ways that you could do these. I like to personally do, I don't know, I call them loops, even though I drew them like triangles in my last class. But anyway, you could just pair up every single pair of these and check all of the slopes between them and make sure they're all the same. That's a bit tedious if you have to do all of them. So the way I do it works. Might look a little silly, but essentially what I do is I like to kind of just look at what's happening between these values. So between 0 and 100, we increase by 100. From 100 to 200, we can increase by 100. And then from 200 to 300, we increase by 100. And then I'm going to check what happens. Why is it over there? With the these g of x, y values as well. So from 25 to 50, we go up 25, we go up 25, and we go up 25. Now this looks like it's probably going to be linear because all of those numbers are the same. But we want to triple check. So essentially the actual thing we're looking for is a change in y over change in x, which in this case is technically a change in g of x over a change in x. But I always remember it as change in y over change in x and then, kind of carry it over to the correct variables for that problem. So in this case, the change in g of x is in this kind of first situation would be 25, and the change in x would be 100, which is why I make those little, again, usually they look more like loops, but now they look like triangles. And then the second situation, we have a 25 over 100, and in the third situation, we have a 25 over 100. These are obviously, hopefully, all the same number. they come out to be 1/4 if you reduce them, right? So since those are all the same number, so this is linear, and it's because it has a constant slope. So we don't really need to check all of the pairings if we just check the pairings between consecutive ones. If we chose any other pairing, it would reduce to the same number if it's a linear function. So this technically, this process is enough to determine if it's a linear function or not. So since it is a linear function, we want to know the equation. So if our equation is, can I kind of bring it back in here? Y equals mx plus b, we need the slope and we need the y-intercept. Well, the slope we actually just found because that was our change in y over change in x. So our slope, I'm going to reduce it though, is 1/4 because that's literally what we're checking to see if it is linear is our slope. And now I need my y-intercept. Well, there's kind of a cheat sheet way to do it in this question. We will talk next class about how to do it if you don't have this kind of cheat sheet way. It's not really cheating, but it's just a shortcut. I should call it a shortcut. It's a little bit of a shortcut way because remember, a y-intercept is when x is 0. So kind of like side note over here, x is 0. Let me actually write the word 0. So in this table, we're actually given the value when x is 0. When x is 0, y is 25. So we have this kind of shortcut where we can just say that the y-intercept is 25. Because the y-intercept occurs when x is 0, and we have the value when x is 0. So since we have that, we have our equation. Y equals our m value, x plus our b value. 1/4 x plus 25. Questions, concerns about that one? Okay. Again, even if I move on to the next one, stop me if you need me to go back to a different one. So for our next table, I'm gonna get rid of that. So for our next table, let's do the same thing. Let's check our change in our t values. So we increase by 5, and then by 3, and then by 7. One other thing you should know about me, I know I'm a math instructor, but my arithmetic is terrible. Pre-calculus, calculus, most of algebra, love it, do it all day. My arithmetic is horrendous. So if I ever tell you that 2 plus 3 is 6, correct me. But anyway. So, and then we have to, so clarification, just because those numbers don't match doesn't mean you stop, okay? I definitely want to make sure that's a thing. So in the last one, they were all 100, which is awesome and a good start. Here, they're not all the same number, but that doesn't mean this might not be linear. So we got to check our change in f of t. So we have an increase of 10, an increase of 6, and then an increase of 14. So remember, we've got to check our quote-unquote change in y, quote-unquote change in x, which in this case is a change in f of t over a change in t. So we've got a 10 over 5, a 6 over 3, and a 14 over 7. If you reduce all of those actually all reduce to 2, so these are actually all the same exact thing. So even though none of those numbers agreed, their ratio reduced to the same number, so this is linear. Yes, it is linear. Same reason, it's a constant slope. I'm running out of space, so I'm not going to write that. Same exact reason. So our slope turns out to be 2, because 10 divided by 5 is 2, 6 divided by 3 is 2, 14 divided by 7 is 2. And then we still have that shortcut, whoops, where we can find the b value because we're given in the table the value when t is 0. So our b value is going to be 10. Now in this case, we need to be a little bit careful. We can use y. I'll say a little bit more about that in a second. But our value for the inputs are t's, so we should put a t. I'm going to erase this for a second and I'll bring it right back. If in that table we were given an actual like variable instead of a function name. So the difference is that this, if I put a D there, that's a variable, not a function name. If they give you an actual variable, you should use that variable. If it gives you a function name like it has in all of these, you can replace that function name with a Y pretty much all the time and no one's going to question you. If you wanted to write the actual function name out instead of Y, that's also perfectly correct. If you wanted to put f of t there instead of Y, whatever floats your boat. I will understand what you mean in both cases. Some other mathematicians might be angry at me about that, but whenever it's a function name, pretty much everyone will be okay with you. Well, at least I will be okay with you switching it over to a Y. But if it actually gives you a variable, make sure to use the right variable. Anyway, last one in this question. So let's see what our x's are doing. It increases by 12, increases by 12, increases by 12. So it looks like it's off to a good start. See what our h of x's are doing. We're increasing by 20. We're increasing by 10. At that point, we could technically already stop, but it's just one more, so let me just do the last one. And then we increase by 5. The reason we could have stopped is since the changes in x's agree, the changes in h of x have to agree, because that's the only way that their ratios will be the same. But technically, let's just go all the way out. So if we were looking at our change in y over change in x, which in this case is a change in h of x over change in x, I shouldn't even be putting an equal sign there. I would get mad at myself for doing that. Those should technically be arrows. Semantics. If you put an equal sign, I'm not gonna like take points off or anything, but semantics, that should technically be an arrow. Anyway, we've got a 20 over 12, and we've got a 10 over 12, 10 over, oh my goodness, 12, and a 5 over 12, which do not equal each other. So this is not linear. Done. That one. We've got 8 more minutes. Cool. Questions, concerns on any of those? All right. I'll wait a couple seconds before scrolling down. We have time for one more, I believe. All right. For each of the following situations, find and interpret the slope and vertical intercept. So for our first one, an icicle grows according to a formula WT equals 0.2T plus 0.15, where T, let me just highlight the things we're going to need. T is a time in hours since the first measurement was taken, and WT is the width in centimeters of the icicle. So we don't necessarily need to find very hard. There's not a lot of work to find the slope and y-intercept. They're kind of just there for us because it's set up in the y equals mx plus b format. So our slope is going to be the 0.2, and the y-intercept is going to be the 0.15. Now, let's get units on that before we try to interpret these. So let's look at the y-intercept first. So the y-intercept is going to be a y value, or a WT value in this case. So those are centimeters. So this would be a 0.1, why did I write an E? A 0.15 centimeters. Now the slope is a tiny bit tricky if you haven't, if you don't think about it in the right way. So remember that this is a change in y over change in x, the slope is, right? So it's essentially has the units of the y values over the units of the x values. So the units of the y values are centimeters, and the units of the x values are hours. So this is going to be in centimeters per hour. Change in y over change in x, y values over x values. Just take the units of the corresponding variables. So if we want to interpret this, essentially what the slope is giving us, now we're kind of going to come back to interpreting slopes a lot when we get to chapter 2. This is kind of like the introduction to it. So what a slope is it's telling you how the function is growing over time, right? So essentially this is telling us if this is about the width of an icicle, it's essentially going to tell us how the icicle is growing. So we would say that the icicle is growing. Growing specifically because the slope is positive. So the icicle is growing at a rate of that slope value, and it's centimeters per hour. So essentially, whenever you're trying to interpret a slope, it's a rate, and it's essentially the rate at which that thing is growing or getting smaller. So if that slope value is negative, then the icicle would be shrinking, would be getting smaller. But since the slope value is positive, it's increasing over time. So we're going to increase. So the icicle is going to be growing. Our y-intercept, if you think about what a y-intercept is, it's when the x value, or t in this case, the t value is 0. So if t is 0, that's telling us that time in hours is 0. So that's essentially going to tell us the starting width. So I would say something like the icicle starts at 0.15 centimeters in width. Questions, concerns on that? All right, last one. I'll wait like 5 seconds in case people are still writing stuff down. For an international travel data plan, a cell provider charges its customers according to the formula CN equals 10 plus 2.05 N, where N is the number of megabytes, so MB, of an international data plan that's used, so the international data used, and C of N is the total charge in dollars for 1 month of international service. So we're essentially just going to look over this in terms of 1 month, because if we get into more than 1 month, then the function would technically get more crazy, but the function we're given would just be for the 1 month. So let's find our slope and our y-intercept. Again, since it's given to us in the y equals mx plus b format, we just kind of pull them off. So the slope, now be careful, it's not necessarily that the first thing listed is the slope. The slope is always the thing next to the variable. So the slope here is going to be the 2.05. And the y-intercept is going to be 10. So the y-intercept is a y value, so that would be in dollars. You could try to shove a dollar sign in the front there. Didn't really have the space. And then the slope, again, since it's a change in y over change in x, we have the change in the y values, so the change in the C of n, so dollars, divided by the change in x, or n in this case, which was megabytes, so it's going to be dollars per megabyte. So if we want to interpret these, again, the slope is essentially the rate at which it's growing or decreasing. So since it's positive, it's going to be growing again, or increasing if you prefer. So this is essentially going to tell us essentially the amount at, sorry. My brain exploded. So essentially it's telling us that the cost is increasing at a rate of $2.05 per megabyte. Sorry. So the cost of the international plan is increasing at a rate of 2.05. I'm going to be lazy and put the dollar sign per megabyte. I should also clarify, the thing that's changing is always kind of the y context. So essentially the first one is essentially the icicle width that's growing. So we can just say the icicle is growing. And this one, since the y context is the charge, it's the cost that's increasing. So that also might not have come across yet. So it's always essentially affecting the y situation. And I've got like 2 seconds to write this down. And the y-intercept would be when n is 0. So essentially the initial cost, even if you don't use any megabytes. So the initial value is $10 before adding any megabyte. So I'll probably talk about that one really quick again on Wednesday because I had to rush through it a little bit because technically we're done. If you need to run somewhere, go right ahead. But if you can stick around for like 10 seconds, I have an important thing to say. We don't have class on Monday, MLK Day. Don't show up, I won't be here. So that means the next time we're meeting is on Wednesday, which we'll also have a quiz. So usually I give you this information on Monday, but since we're not meeting on Monday, your quiz on Wednesday, and I'm typing this out in chat, will include questions like, is this a function? So we'll also go over some of those at the very beginning of class on Wednesday. And we will also, I will also ask you questions on, is a set of data linear? I can't spell data. So I just put that in chat, and that will be things like these tables we did here. So you'll have your first kind of official quiz on Wednesday on those two topics. Your first official homework will appear on Monday. Of course, you don't need to start it Monday. You have a whole week to do it, but it will pop up on WebWork on Monday, even though we don't have class. Otherwise, if you have any questions, feel free to stick around for a little bit. Otherwise, have a great weekend, extended weekend. Have a great day, and I'll see you on Wednesday. Thank you. You're welcome.